It is such a pleasure today to be here with Professor Peter Atkins, who I have long admired, and it's wonderful to have you join us to talk about your career, your amazing work, and talk some chemistry as well. How are you doing today?
Oh, all right. I think that's overselling me, but there we are.
Yes, I know, but you've been quite understated. I had the pleasure of working with you in person back in November when you very kindly came to our town and had a very interesting chat with Keith Fox about science and religion and the future. And it's a real pleasure to catch up with you again. What are you doing these days at Oxford in terms of chemistry? Are you still involved in research and teaching at all?
Well, I retired in 2007, so that was ages ago. And since then, I've continued to write, and I'm still writing, and um, that's what I do every day, and it seems all day.
Well, I get the sense it's something you particularly enjoy. Are you still engaging mostly in textbooks and the teaching of chemistry, or is it more popular writing?
At the moment, it's textbooks, so I've got three on the go at the moment. Um, I can't say what they are yet, but they are a full-time occupation. And I find it invigorating, a pleasant way of passing the time. It's always a writing is always an encouragement to learn, both to learn what one's writing about and how to write about what one is writing about. Uh, and the textbooks just need to be kept up to date because um, the subject evolves, not very much, but enough to um, take into account. The audience evolves much more quickly than the topic because students come with different attitudes and different abilities, and one has to try to match presentations to their ability to absorb and their ability to take pleasure from learning. And also the technologies of education and authorship are constantly changing. So I have to keep up to date with the way that books are prepared, how illustrations are done, how calculations are done, things like that. So um, it's a, it's a constantly fluid environment that one is writing in.
I imagine that's an immense challenge because science never stands still. I mean, there are certain factors, I'm sure, in chemistry, as with physics, where there are some things that won't change and they're not about to change, and there's no scientific revolution on the horizon that's going to overthrow the laws of chemistry. But science is always on the move, and
Yeah, but it depends on which science you're talking about. My textbooks are mostly in the region of physical chemistry, which is the um, interface between chemistry and physics. It's where chemistry takes its principles from, and its principles really lie in quantum mechanics and in thermodynamics, with a smattering of chemical kinetics, the rates of reactions, and so on. But the kind of thermodynamics and quantum mechanics that chemistry draws on really haven't changed very much since the 1930s. So it isn't, I'm not under the same pressure to evolve, to keep up to date with the principles. It's when you come to applications, different types of spectroscopy and so on, different types of colorimetry, that change takes place. But those are very much on the margin of quantum mechanics and thermodynamics. So basically, fundamentally, I have quite an easy time.
I'm sure you make it easy, Professor. How long have you been at Oxford and involved at Oxford?
Um, I was appointed in 1963 and told to go away for a year to grow up. So I went to UCLA to do the growing up at University of California, Los Angeles, for a year, and then came back into my first and only job here in 1964. And I stayed in Oxford doing effectively the same job, or at least more or less the same title, for 40 years. So I did not personally progress.
Well, yeah, some people would look at that as a job well done, Professor. When you over 60 years in the same place, and they say there's no such thing as a job for life anymore.
Yeah, right.
When did you write your first book?
67. Do I mean that? No, I don't mean that. It was published in 1967, a little bit before. I was writing it while I was doing my my postdoc in UCLA. It was, in fact, a book that worked up my PhD thesis into a monograph, and I wrote it together with my then supervisor at Leicester, Martin Simmons. And so that was the first book. The first textbook was molecular quantum mechanics, the first edition of which was published in 1970, and I did that on my own.
Right. Could you let's get a bit more into your background. I'd love to know how you fell in love with chemistry and how you knew that it was going to be your future and what you wanted to commit your life to researching and teaching.
Well, I think those evolved, but I think I can trace it back to my high school days, grammar school. I was at Dr. Challoner's Grammar School in Amersham in Buckinghamshire, um, where really we did the classic triumvirate of chemistry, physics, biology. Physics, I think I was finding too mathematical for my taste at the time. Biology, I think I was finding too embarrassing because things were having sex all the time, which for a
Terrible,
pubescent
isn't it?
youth, that was not something I really felt comfortable with. And so that left something in the middle, chemistry, which was neither embarrassing nor too mathematical. And I think I found myself in my correct intellectual milieu at the time. And then um, uh, I decided really that chemistry was something I wanted to pursue. There is a kind of side track to this account because I dropped out of school at 15. In those days, one could. Speaking of hundreds of years ago, basically. And I went to work for Monsanto Chemicals as a lab assistant for 2 years. And they increasingly, I think, got fed up with me and encouraged me to go back, find a way of going back into the university system. And by a sequence of lucky chances and judgments made by people to whom I'm eternally grateful, the University of Leicester sort of drew me back into the system. And I went to Leicester to read chemistry in 1958. And found it to my liking. Stayed on to do a PhD with the person I mentioned a few moments ago, Martin Simmons. Found that increasingly to my liking. And once you get trapped into the university academic life, no other life is really very appealing, because it gives you, intellectual freedom. At least they did in those days. They are horrid these days. For example, when I reflect on my career, I really have never had a boss to tell me what to do, except when I was that lab assistant for Monsanto. I've been autonomous throughout my career, and although the form of the job at Oxford didn't change, I was always tutor in physical chemistry at Lincoln College, which I found a very moulding, rather not mouldy, moulding experience. And for the university, I was university lecturer in physical chemistry, later reprogrammed to Professor of Physical Chemistry. But throughout, I was my own master, effectively. And that, in a sense, looking back, was enormously valuable as a way of spending one's career. Who wants a boss, after all?
Yes, absolutely. Um, so, was there a particular moment when you were a child that chemistry really became an attraction, or do you put most of it down to having an excellent teacher and landing in a situation in Leicester where you were really switched on by the environment?
Well, I have to admit that I did have a chemistry set when I was a child. And so um, I presume it was full of all sorts of poisons, and I suppose totally illegal now.
I imagine so.
But it was a great stimulus to messing around with things that changed colour and stank and got stuck on everything. So that must have been the germ of my interest in the subject. But my um, reflection on the unconscious wisdom of choosing chemistry is that, as people say, it is the central science. And as such, it puts you right in the middle of the sciences. And so, as you progress as a chemist, you find yourself reaching down into physics for explanations. You find yourself reaching out into biology and material science for applications. And you find yourself having to master mathematics in order to render qualitative ideas quantitative, to give them enough spine to stand up to experimental checking. And so it's a very valuable central place in the scientific universe to inhabit.
Yeah, that's absolutely wonderful. I love the way you've put that. It must have been a really interesting time, the second half of the 20th century, being in chemistry, particularly somewhere like Oxford. I mean, I can speak only mostly for biochemistry, but you've got the birth of molecular biology. Obviously, a lot is going on with quantum physics as well, and it's being applied more broadly. What was it like working at Oxford in research and in teaching in chemistry at that time?
No, invigorating. I mean, it's one of the biggest chemistry departments in the world, um, and with massive schools of physical chemistry, inorganic chemistry, organic chemistry, biochemistry, material science. It's huge. Even if you just limit that to the classical chemistry departments, physical, inorganic, and organic, it's got hundreds of DPhil students and so on. hundreds of faculty, basically. It's enormous. And the advantage of being at a honeypot like Oxford is that there's a constant stream of visitors passing through, both casually and for extended periods. So it was a intellectually vigorous place to be, and not only in the sciences because of the collegiate structure of the university. It means that when you're having dinner at night, in the evening after having done, like I say, a couple of hours of tutoring very bright, extremely bright, embarrassingly bright undergraduates a lot of the time. And then you find yourself in the company with historians, poets, musicians, and having that kind of breadth of intellectual interaction outside the demands of the yet very exciting chemistry department.
Yeah, gosh, I can only imagine the things you must have been able to see and be around. Very exciting time. Did you get to supervise a lot of interesting projects? I know you were committed to teaching and writing a great deal, but did you have many students under your care in that time?
Well, divide that into college and university. As a college tutor, I was responsible for, let me say, well, we took 6 undergraduates a year. So we saw them, those 6, through their entire course. The 3 years of undergraduate and 1 year of project work, basically. But basically, we were looking after them for those undergraduate years, seeing them for an hour a week, seeing them outside the university for various ways, very intimate kind of interaction. And I'm still good friends with some of my pupils from my very first years in the
Wow.
1960s. They've all retired by now, of course, but it's quite extraordinary when one got to know them very well, one thinks, and
I
certainly stayed
yeah,
in touch.
I met a.
Go
Sorry,
ahead.
go ahead.
Now, in the university, of course, one's responsibility is for one's graduate students, one's people studying for what we call DPhil, a PhD in common language. And in the early days of my tenure, I did have quite a substantial group with about 10 graduate students reading towards their DPhil. But when I found in round about 1980 that my books were demanding so much of my attention, I decided it was improper to take on those young minds and not give them my full attention. So, in essence, I closed down my research group and switched to full-time writing, but doing my lectures and things like that, and certainly continuing with my college duties.
Yeah, I met a gentleman in passing back in January who had been a student of yours, and he was just coming up to retirement age, and just in passing, I found out that he did chemistry at Oxford, and I said, "Was Peter Atkins your professor?" He's like, "Oh yes, Peter Atkins was my professor. I remember it well." Um, yeah, what a legacy you've had over these years. Just moving on, one of the things I really love about you is you've been a champion of science and rationality and reason for your whole life. We're at an interesting point in history at the moment where, on the one hand, science is really moving forward at such a rapid rate, and it's so exciting thinking about the future. And on the other hand, we've got sort of quite a distrust in science and authority in the aftermath of the pandemic. Why should people still study science, and particularly chemistry? And could you speak into what you're excited about with the future?
Well, you mentioned the pandemic. If there hadn't been the science that was being done then, most people who were complaining about science would be dead.
Yes.
So, don't knock science. Science enables the modern world. I know it has some consequences that are undesirable. Those are commonplace undesirabilities like environmental pollution, weaponry. But think of what science has done to enable us to have the lives we do. Travel transformed, communication transformed, lives not only ameliorated but prolonged. Agriculture transformed. Uh, it's effectively beyond measure. And all this is done because people gradually realized that thinking for themselves, but relating their understanding to observations that could be made and shared with others was worked. I mean, I often think, and maybe I've said it, but I think that science really began in about 1492 with the discovery of America. Not because of America and the contribution of its science, but suddenly there was this extraordinary discovery of something that hadn't been mentioned in any holy book. You don't find America mentioned in the Bible. You don't find America mentioned in the Quran. So here was something that is not in the books, something that is there to be explored that people didn't know about. And in a sense, that's what science is all about. It's going out there and exploring in a controlled way what there is out there. Um, and there is, of course, a degree of authority in science because you don't want to reinvent the wheel every time. So you have to accept maybe that wheel should be round in order to get to work pretty well. So you accept certain things. But if you, in due course, find that runs counter to experience, then you dump the idea and you move on to another idea. Science is all about getting it wrong, but recognizes that it gets it wrong. Religion is all about getting it right and knowing that it's right. Science is all about getting it wrong, knowing that it's wrong, but repairing it. And really that's sort of a major difference between them. Science is a force for good. It's a unifying cultural activity. You don't have Japanese science. You don't have sort of American science. You have science. People say that music is the universal language, but science is much more universal than music. I mean, listening to some of the noise that passes for some foreign language, some foreign music, it really, that it's pretty awful. I'm not getting on listening to that. But science, wherever it stems from, provided it is tested against experiment, tested against reality, if you like, gradually thereby exposing what we mean by reality. I think it is a universal language, and such a simple thing. I mean, why did it take thousands and thousands of years for people to stumble upon the mode of doing science? That is, to think about what you observe and to set your ideas about why things happen in a reticulation of other ideas. So, chemistry, you can't do biology without chemistry these days, even more so since 1953. I mean, it
Yes.
used to be nature walks, and now biology is really molecular biology, which is just a fancy name for chemistry.
Yeah,
Um,
absolutely.
yeah. Um, as I was saying earlier on, being able to be in the centre of science in chemistry and draw on explanations and applications and quantifications. Um, it's it's really a part of the scientific ethos to communicate universally.
Yeah, just looking at the last decade of Nobel Prizes, and looking at where we sit right now on the frontiers with artificial intelligence, spacefaring, robotics, genetic engineering. Um, is there anything in particular, looking at the future, that you're really excited about in terms of scientific breakthroughs?
Oh
What
yeah,
the next?
yes. I think there are only two big problems in science. Lots of little ones like curing cancer and things like that. But um, the really double whammy sciences. One is where it all came from, and the other is um, how do we know? In the sense that, let me gloss that. Where it all came from, I mean, I think cosmology, cosmogenesis, the origin of this something out of nothing. How did it happen? Not why did it happen. Why is never a proper question in science. But how did it happen? How did nothing suddenly tumble out and turn itself into what seems like not nothing? So I think that's a big question, and it's people are making sort of progress. String theory, people think that still might be a clue to the way forward, but it's got and relatedly, quantum gravitation is still in the mud. But scientists are beavering on, haven't given up. And but what I meant about how we know about it, I meant the nature of consciousness. Um, so having got stuff out of nothing in the event of cosmogenesis, and that event having evolved into we thinking things, we lumps of intricate matter, sufficiently intricate to be aware of our own existence. Quite extraordinary that.
Yes.
Uh, 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 to solve the question of consciousness. And I think the two questions will have different types of answer. I think it's pure speculation now. Um, Cosmogenesis will be a mathematical elucidation of what happened, and we'll have a lot of trouble because of our minds are built in the farmyard, basically. So we have trouble interpreting mathematical structures in terms of physical models. I mean, even current quantum mechanics is difficult for us. Our brains are constructed to respond to snakes and tigers and animals and things, not taught, they haven't been involved in the context of overt quantum phenomena. That's why we find it so difficult to think about what entanglement means, and superposition and all that sort of thing. But we can do the maths. No problem with the maths. So I suspect that in due course we'll have a mathematical theory of cosmogenesis. Then when it comes to consciousness, the answer will be different. It won't be an equation. It will be a model, a simulation. Whether that will be a simulation based on current models of computation or not, I don't know. Whether it will be essentially involve quantum mechanics, I don't know. Perhaps it will need a quantum computer to understand quantum mechanics. Who knows? So I think, and we're edging towards it. Look at what you can do with computers these days. See, I don't even know if you're real, and maybe you don't know. Perhaps if I'm real. So,
I noticed you talked about consciousness and the origin of consciousness and the origin of the universe. I just wondered if you had any thoughts on the origin of life as a chemist, maybe
well,
perhaps in the intersection of them.
yeah, that's a pretty easy question, really, even though it hasn't been solved. I mean, there's lots of ideas about how the inorganic flipped across into a pretty accurately self-recreating bit of matter. That's what life is. And so you can see, put that way, it's not hard to see that it's moderately easy for it to happen. It's probably quite difficult for it to survive because all sorts of natural cataclysm could overwhelm early life. And it's even more problematical about how life can evolve to our level. And whether it evolves further on, of course, is open to question, given the fragility of both our environment and our societies. And almost certainly we're not alone in this universe, but equally, almost certainly, other life forms are so far away that we will never have direct contact with them.
But these are big questions, but you're quite hopeful that we could land on an answer in
Oh
the
yes,
coming decades.
oh yes. I mean, there's another contrast between religion and science. I mean, religion says that all the answers are beyond human comprehension. Don't even try to understand the Trinity. Don't even try to understand transubstantiation. Don't even try to understand life after death. That's not to try, because none of those things exist anyway. But at least it's uh, it's denigrating human competence. Whereas science takes entirely the opposite view. It's out there to understand. Okay, limited brains we have, but nevertheless, let's use them to their full extent. And let's not be thwarted in our aspiration to understand by naysayers, people who denigrate science for their own often religious ends.
Hmm. It's so wonderful to have you here today, and I really hope some of our students and those listening will be inspired. I just want to ask you a final question about. I mean, you've mentioned your teacher who really helped you and encouraged you, but was there anyone else when you were young or early on in your career who really inspired you to pursue excellence in chemistry?
Yes. Funnily enough, yesterday And I don't know whether yesterday will then mean anything to people who in due course will see this. May the 7th, day before yesterday, May the 17th, 2025, to pin it down for future generations. I went to my alma mater, University of Leicester, where they were celebrating the centenary of their chemistry department. And I had to give a talk, which really was entitled "What Leicester Chemistry Did for Me." So I'm edging towards answering your question. And I identified 3 or 4 people. Incidentally, it was for me being nearly as old as the institution whose centenary I was celebrating. But that's by the by. I identified several people and institutions, of course. I identified what they were then called personnel manager at Monsanto, who, either to get rid of me or in recognition of something or other, urged me and encouraged me to go to university. So I would never have done that without him, and I would not become what I did become. I have no idea what I would have become, but there we are. I would also put down a very important person in that sequence, the lecturer at Leicester, who decided, and I do know this from later conversations, to take a risk with me and offer me a place, even though my A levels were beyond awful.
Wow.
And so it was she, that was Florence Shaw. I think my PhD supervisor, Martin Simmons, at Leicester, was also a very important developer of what I think I would say is my scientific insight and my love of science. And so those, I think, are the principles. I'd also say that my postdoctoral supervisor at UCLA, Dan Kippelson, was instrumental in setting me off on my career of theoretical chemistry. And he had a very engaging way of thinking, which he was a physicist more than a chemist, and I think that's rubbed off on me. And I suppose beyond them, all my undergraduates and students who forced clarity out of obscurity.
I love that. That's such a wonderful answer. It's been such a pleasure to be with you. I really hope that some of the students, young or old, who hear this are inspired to think about reigniting a fire in chemistry. And it's always a pleasure to talk to you, Professor.
Simon, it's a pleasure to talk to you as well. Thank you very much.
Thank you so much for joining us.
Goodbye.